Hello, I am Abhinav Sharma. Welcome to Python Wife. Now, we have in the previous example, we saw that only one function was being performed on the input. Now, what if there are multiple functions are being performed on the input? Previously, we have a single input and we are using a single for loop or a nested for loop in a same loop, in a same function. But this time, if those functions are multiple, what we do, how do we find the complexity of those complex functions? So in the example you can see here, there are several tasks which are being performed. First, a string is printed 5 times on the console using the print statement. Next, we print the input list twice on the screen, and finally another screen is being printed 3 times on the console. To find the complexity of such an algorithm, we need to break down this algorithm into parts, and then we will try to find the complexity of those individual pieces. So now let us break down this script into individual parts. So here you can see this first part. The complexity of this first part will be O of 5. Why? Because Python is awesome. This line is printed 5 times. So since 5 constant steps are being performed, this will be O of 5. Next, we have this for loop. So we know that the complexity of the above piece of code will be O of n, because we have performed the example, we have performed this experiment into our code editor. So we know that the number of iterations are equal to the number of items, right? So complexity of this second part will be O of n. Similarly, the complexity of the third part, the final piece of this code, will be O of 3. Why? Because this print statement is being executed 3 times, where 3. And finally, how we can find the overall complexity of this algorithm. So for finding overall complexity, we just need to add those individual complexity. So for this, it is O of 5. For this, it is O of n. For the third piece, it is O of 3. And for the fourth piece, it is O of n again. So O of n plus O of n will comes to O of 2n, and O of 5 plus O of 3 will go to O of 8. So we said earlier that when the input becomes extremely large, the constants becomes insignificant. Means we do not need to count the constants when the input goes very large. Therefore, we can ignore these constants, right? So we will ignore O of 8. So the complexity which remains is O of 2n. But here 2 is again a constant, because the complexity when goes to insignificant length, 2 will not be counted. Twice or half of the infinity will still remains an infinity. So the final complexity of this complete algorithm will be O of n. Now let us understand what are the worst and the best complexities. So usually when someone asks you about the complexity of the algorithm, he or she is asking you about the worst case complexity. So to understand the best case and the worst case, we will look into this for the script which is written on here on the screen. So here you can see we have a function that takes a number and a list of numbers as an input. It returns true if the past number is found in the list of numbers, otherwise it will return none. So for example, if you search number 2 in the list, it will be found on the first comparison, right? So this will be the best case, when the number which we need to find, we found it on our first iteration. So this is called as best case complexity, and this will generally be O of 1. Why? Because we just iterated one time and we found the result. On the other hand, if we need to find the 10, it will be found at the last searched index. So the algorithm will have to search through all the items in the list. Hence the worst case complexity will become O of n. Why? Because number of iterations will be equal to the number of items, and 10 is situated as the last item. So the iterations that should be done is n times, where n is the number of items. So this is the reason why the worst case complexity here becomes O of n. In addition to best and worst case, we also calculate the average complexity of an algorithm. So this average complexity is generally the random input that we pick up from the list from the input. Another thing is, till now we are covering time complexity, we are calculating time complexity. There is another parameter of the complexity, which is space, where we count the number of steps required. And in the space complexity, we generally found the number of spaces actually we need to allocate in the memory space during the execution of the program. So for this, let's have a look into the following example. So in this script above, the function return spaces, it accepts a list of integers and returns a list with corresponding squares of those integers, right? The algorithm has to allocate a memory for the same number of items as in the input list. You can see we have mentioned here an empty array, and this list will store all the elements which are in the input list. So memory needs those space. Therefore, the space complexity of this algorithm will become O of n. Why? Because the length of this squared list, the new list, will be equal to the input list. So if the input list goes to n, automatically the squared list will also go to n. Let us find out the time complexity of a recursive function. So before that, let me tell you, there are generally two ways or two approaches or two methods to find the time complexity of a recursive function. The first one is successive substitution method, and the second one is the master theorem. So before digging deep into finding the complexity, let me give you the idea behind one. Suppose there are some books kept in one place and you have to move the book and keep it on the shelf or in a rack. How much time do it take? Maybe half a second or quarter a second. Maybe if somebody walks very slow, it takes 1 second for keeping one book. So the time varies from person to person. Similarly, we assume that every statement in a function takes 1 unit of time. If that statement is repeated multiple times, then we need to count the frequency, that how many times it is executed. That is sufficient for analyzing our function. So for that, let us take an example of a recursive function. So here you can see the following function. That is, we will calculate the time complexity of the following recursive function. Now let us see what the above function fun1 is doing. It is doing nothing, just printing. It is just printing the value of n. Now how much time does it take for printing? It takes 1 unit of time for the printing, because I said every statement takes 1 second or a 1 unit of time, and here we can see there is only one print statement. But this is a recursive function, so it is calling itself again and again. Now, as it is a recursive function, let us find out how many times the printf function is executed. Now, to find this out, we are going to see this tracing tree, or we can also say this a recursion tree. Now you can see in this above recursion tree, first it prints the value 3, right? Then prints 2, then prints 1. That means the printf statement is executed 3 times. So this recursive function will take 3 units of time to execute when the value of n is 3. Suppose what if the value of n is 5? Then it will take 5 units of time to execute. So we can say for n, it will take n unit of times. Now coming back to our example, if we have to keep one book on a shelf, we will take 1 unit of time. For 10 books, we will take 10 units of time. So for n number of books, we will take n units of time. The most important point that we need to remember is that time depends on the number of books. the time can be represented in the order of n. Now let us find the recursion function's time complexity using the recurrence relation. Now there is one more method to find the time complexity, which is recurrence relation. Let us see how to write a recurrence relation and how to solve it to find the time complexity of the recursive function. We assume that the time taken by the above function, this function is t of n, where t is for the time. If the time is taken for fun1 is t of n, then the total time should be sum of all the times taken by the statement inside that function. So let us look at the statement. Every statement takes 1 unit of time. See, there is conditional statement which says if n is greater than 0, how much of time will it take for the execution? Again, it will take just 1 unit of time. Now there is a print statement. This will again take 1 unit of time. Then there is a fun1 n minus 1. Now how much time will it take? It will again take 1 unit of time. But this time it is not correct. It will not take 1 unit of time. This is a function call. This is not a statement. It should be total time taken by that function. It is not just a normal statement. It will call again itself. So we need to know how much time will this function call will take. Let us see this closely. What we said that fun1 and int n, the total time it will take is t of n. Then what time will taken by fun1 n minus 1? It will simply be t of n minus 1 because the value of n is decremented to n minus 1. So let us take the sum. So what will be the sum? It will be t of n is equals to t of n minus 1 plus 2. So for better understanding, look into this image. The recurrence relation, this is known as the recurrence relation that we find out. It will only stands if n is greater than 0. Now what happens if n is equal to 0? So here you can see what will be this condition, how to check this condition. If n is equals to 0, it will again take only 1 unit of time. So this recurrence is formed from the function 1, and the time complexity of the recursive function can be represented in the form of recurrence relation as well. Now let us look into another method of finding the time complexity of a recursive function. It is oftenly used and it is one of the most easiest way to find the time complexity of a recursive function. It is known as successive substitution method or induction method. We can also solve this example, the example that we have created. This example using the induction method as well. So let us solve this one. Before solving this, we should know one thing, that if we have any constant value, then the value will be 1. In our example, the constant value is 2. So we will replace it with 1 as shown in the below diagram, right? We will replace this plus 2 with plus 1, all right? So our recurrence relation will look like this, which we have written in equation 1. T of n is equal to t of n minus 1 plus 1. Now we can also solve this if we know that t of n minus 1. Now what if we need to find t of n minus 1? So we will replace t of n with t of n minus 1 and it will become t of n minus 1, and here n minus 1 will make n minus 2 plus 1. Now we will substitute this thing to the equation 1 and it will make equation 2, which is t of n is equals to t of n minus 2 plus 2. Now let us also find out t of n minus 3. So for this we need to substitute our n minus 2. So when we do it, we will form an equation 3. You can see t of n is equals to t of n minus 3 plus 3. So by a simple substitution, you can simply understand what is happening here. We have substituted 2 times. So how long we should do this? Let us assume that the last number is k. So we will proceed till k. So instead of 3, when we proceed till k, it will become t of n is equals to t of n minus k plus k. So go on substituting until it reduces down to a smaller value, that is n is equals to 0. When we don't know the answer for the bigger expression, then break the bigger one into smaller one. And this is the concept of recursion that we have discussed in our previous videos. The same thing we have done, and we don't know how much this is, but we know when n is equals to 0, then the answer will be directly 1. Now we see that this is n minus k actually has become 0 when we put k is equals to n. When we put k instead of n, you can see t n will become 0. And finally, we know that when 0 comes, it will return 1. So the final output will be 1 plus n. Now this 1 plus n can also be written as O of n, because we know in big O notation we generally ignore the constants, because constants don't hold the values when the values are infinitesimally large. Earlier, directly from this tracing tree, we also have seen n plus 1 was the number of calls, and time taken by the function depends on the number of calls. So this will simply results in finding the complexity of the recursive function which we have discussed as O of n. So we have discussed 3 methods how we can find the recursion function's complexity. First is the tracing tree. You can see the second method is the recurrence relation, and the third method is the substitution method. So from all these methods, the output will be the same. O of n will be the complexity of this algorithm. You can use any algorithm you prefer to, or you love to, or which is easy for you to understand. Thank you for watching. For more such videos and detailed explanation, visit pythonwife.com.